I heard 1-0. Sorry. 5-0?
Yeah, 5-0.
Wow. Well, they're gonna be aiming for you, so you know that.
Yeah.
All right. So let me just check off the peeps at home, make sure I got everybody, and then we'll get rolling. Anthony's here. Josh is here. Heck and darn. Come on, fingers. There we go. And, oh my gosh. Usually it's in the morning. Sorry. Good. And Isabella. Okay, all my home peeps. Thank you. And all my other peeps are here. So we're good. Great. I apologize. I didn't post Wednesday's calendar, but hopefully you figured out to do the Ed puzzle on your own. And I also apologize because I spelled VSEPR wrong. Oh, well. The lab, I finally got around to grading it. I totally spaced out about it because I didn't put it in Aries right away. And so I had the pre-lab in there, but I didn't have the lab. And then I so the little dropper bottle lab that I did when I was still at home, I'm really sad because there was a fair amount of shared information, it appeared to me. In particular, one way I know for sure is there was a really blatant typo on some of your papers, bios, cyanide, with a 0 after it. And then there were some other pretty obvious similar boo-boos. And so when I see the same exact boo-boo, I didn't have the time to go and get all of you, and it wasn't that many people in here, but I notice the stuff, and I want you to know that I notice, even though I don't always do anything about it. And please do your own work. It does you no good to copy stuff. Okay? It does you the immediate get the points, I guess, but it doesn't help you later, and all of this stuff builds. So we're going to have to go back and do another ion lab because there was some confusion on what should have been done on there. So I will have one of those for you next week. So we're going to go back again to chapter 7 stuff, but that's okay. Correct. Correct. Okay. And you can look at it and find out why, and I'll be happy to talk to you about it. That's the other thing. I'll meet with you guys. You just have to let me know that you're having trouble. I'll talk to you. You can set up stuff on Wednesdays. I've done Wednesday office hours. I tried it again at the beginning of the semester and people didn't show up again. So it's like I don't know. I don't know what to do. But if you email me, I will get back to you. Also, late work, not so much in this class, but in the others. I just got to cut that out because it's so hard for me to go back and find it all and check back on it. And yeah, at some point, it's really, what's the point of doing it? Because you needed it for an assessment. So I'm going to come up with a plan and I'll tell you on Monday because I didn't get to it yesterday. All right, enough of the crabby stuff. So what we're doing today, we're not going to do this. This showed up in your classwork as one of the things. We'll do it tomorrow. We're going to put our knowledge that we gained today and what you gained from yesterday to use building some molecules. But you will want this graphic organizer if you were smart, and those of you in this classroom, I would have out a piece of paper and a pencil and turn the paper sideways and just kind of take notes. And then this isn't for me. You're not turning it in. It's for you knowing how to do this stuff and understanding what's going on. It's a lot easier if you draw the shapes. So I would strongly suggest that. And then those of you home, you're welcome to do it on your own paper or do it however you like. You don't have to do it at all, of course, but it will help you, I promise. Okay, so there's no homework. Didn't post that video. Uh-oh. I don't, but I need a parent if you want, that's, yeah, you should really have someone call the office so you can get that cleared because it's your attendance for yesterday. So if you didn't get on yesterday, you're absent. Oh, yeah. So Wednesday assignments are how we take attendance. So you need a parent to call in and clear that. Okay. Yeah. It came at 8 o'clock, didn't it? What's that? Yeah, that's all it was. No, I posted it at 8 o'clock. So if you didn't see it, then have somebody call in or whatever, send me an email, okay? Because I posted it at 8. It should have dumped into your feed. It was scheduled to go in at 8 o'clock in the morning, way before our class. Okay. Have a parent call in, okay? Or email me, okay? So did everybody get it at 8 o'clock or in the morning? Yeah. Okay, so if it didn't show up, and maybe it's that different device thing that we have put it with before, I don't know. Okay, so yeah. Okay, so let's get rocking and rolling. And oh, my daughter asked me to find this video. Have you guys ever been whale watching? Have you ever had whales go underneath your boat? They did. It was so cool. Sorry, you don't need to listen to us. Oh my god! Oh my god! So you can see them starting to circle, and then there's always a lot of birds. So they chum all the fish into one hoop. See? We were in this little tiny. We went on a cruise to Alaska, and we were in this little tiny. Watch, here they come. That's my daughter. That's what everybody says. I don't hear it, but no, that's my 11-year-old at the time. So they're just eating all the fish that they scoop together. That was her. That's my husband. And this is my really bad videoing. I mean, we were like, could reach out and touch them, and then they went underneath the boat, and then we all go running through the cabin. It's pretty funny. So cool. That's me. Good old Chessie. There. Oh. Anyway, we got sprayed by the whales. It was so cool. Anyway, sorry. Thank you. It's a once in a lifetime experience, that's for sure. Ooh, I got goosebumps again. All right, sorry about that. Thank you for letting me go down memory lane. Sorry. Oh, I know. Sadness. They took all the baby goats away. I know. We go home Tuesday night. No baby goats anymore. Oh well. It's okay. That was fun while it lasted. All right. We are talking about VSEPR. Don't peek. And hopefully you learned yesterday that VSEPR stands for V for V for Valence. Say it loud like you mean it. S for S. S. Shell. E for electron. Good job. How do electrons like to live? Paired. And they're all negative, so they repel. Valence shell electron pair repulsion is what VSEPR stands for. It's a lot easier to say VSEPR than it is to say all those words. And so we just smash it all together and say VSEPR. So instead of VSEPR, VSEPR. The underlying assumptions is that electrons are going to form bonds in pairs. Usually, not always, one electron from one atom, one from another atom to make that single bond. There are multiple bonds possible, so you can also have single bonds. And that's these are little chemistry tinker toys. So they're wooden spheres that have holes drilled into them that represent the valence electrons that are available for bonding. And so the single bonds can happen. We have to use springs for double bonds and springs for triple bonds. So we can have multiple bonds between atoms, certain atoms, not all of them. Carbon is notorious. And then also some atoms have what we call lone pairs. What's a lone pair of electrons? What's that mean? Obviously it's a pair, so it's two. They are not covalently bonded. What are they doing? They're just hanging out together, right? And they're from the same atom. So lone pairs of electrons are two electrons from one atom. Normally in a bond, one electron from this atom, one electron from that atom to make a bond. Why do we have to learn this stuff? Well, you guys already know a little bit that shapes of molecules determine their function, determine how they can interact with other things, like getting across a cell membrane. We're not going to deal with huge 1,000-atom molecules, okay, like proteins. We're going to deal with little baby molecules, maybe a dozen tops atoms. Okay? However, the shapes of molecules will influence how they behave. So water is a super small molecule. It shouldn't be a liquid at room temperature, but it is. Okay? Why? Happens to be because of its shape and the lone pairs on it. Nitrogen with 3 hydrogens, ammonia, also has a different shape than you might expect because of the lone pair. And that determines how it's going to dissolve in other things, how it's going to be a solid, liquid, or a gas at room temperature, all sorts of stuff. So understanding molecular geometry is important to understand how things should interact and to have the basis of it. What's really cool is we can get a lot of information just knowing where the central atom lives on the periodic table. Again, electrons are going to want to hang out in pairs, but they repel each other. And so in those pairs, they're going to try and get as far away from each other as they can in 3-dimensional space. Our world in school is flat, okay? Flat screens on your Chromebooks, flat pieces of paper. Real life's 3-dimensional, and so there's a little bit more than you might expect, and it's hard to see things, at least for me, on a flat piece of paper in 3D. Lone pairs also, in addition to coming from the same atom, they also take up more space. The reason for that is there's no other atom's nucleus pulling on it or doing anything to it. So this cloud of the electron pair, I'm doing my little electron pair on nitrogen, it can exert more of a force field to these hydrogens because there's not a nucleus of another atom pulling on them. And then also double and triple bonds take up more space. And that kind of is a no-brainer, right? 2 electrons versus 4 electrons versus 6. The more you have, the bigger cloudy area of negativity is going to be. This is a gentleman who is a professor of organic chemistry at a college in Texas, Dr. Paul McCord. He doesn't cover all the shapes, but I don't know why that just came out. He doesn't cover all of it, but I want to share this with you because they have some, I think it helps seeing their graphics moving around. So.
How to write electron dot formulas on a piece of paper, which is a flat sheet, and you're kind of limited to the 2-dimensional world. You have to really start thinking about how molecules really look in a three-dimensional world because that's the world that molecules actually live in. The simplest model for modeling this type of behavior, and it actually works rather well, is called the valence shell electron pair repulsion theory. And the name's probably scarier than it actually is as far as it works. We often just call it the VSEPR theory, and then we kind of just say it all together, VSEPR theory. So you'll hear me say VSEPR theory from now on when I mean the previous. So the way it works, and the name kind of gives it away, is you take your electron dot formula and you simply count electron regions around the central atom, and you realize that each of those regions is a negatively charged region. And so it's going to repulse all the other negatively charged regions, and they're going to try to get away from each other. They can't completely get away, though, because the nucleus of the central atom is holding them in. So what they do is they try to get away from each other, but they're still held by the central atom. This leads to distinct molecular shapes. And the easiest one is two regions. If you only have one atom on one side and one on the other, and they try to get away from each other, you get a fairly linear.
So I mean, I really like the graphics, but they show the central atom as a circle shape, which is kind of how we usually represent it. But then this looks distorted. So this is the shared hybridized cloud. There really, I think, could be two more atoms. So he jumps right to the central atom plus two more for a total of three. And you can't really have a central atom if you only have two, but it is possible for this a binary compound, right? Just two different atoms or the molecule of the two of the same atom. So that would only have two, and that would also be linear.
Molecule. And so that's the first one. Two regions gives you linear shape. The bond angle is 180. Stepping up to the next one, three regions. You count the regions around the central, there's three. If three regions try to get away from each other, you basically get a nice kind of pie shape, like taking a pie and cutting it into perfect squares. So you get a 120-degree angle all the way around to those three regions. Both of those regions are still planar. They still look just fine on the paper. It's when you get to four regions that you have to go to the third dimension. You have to go three-dimensional. And what this gets you is a shape that we call a tetrahedron or tetrahedral geometry. There's four regions around the central, all perfectly symmetric. And if you take a look and spin the molecule around and look at it, every region is equivalent. And the bond angles are now down to 109.5 degrees. That's the tetrahedral geometry. So as you can see, the bond angles are getting smaller because we're bringing in more regions. We started at 180 for linear, 120 for trigonal planar. Now we're down to 109.5 for tetrahedral. So that really sums up most of what we will use, especially in organic chemistry. Now, in addition to those, you can have expanded octets, which gives you 5 and 6 regions. So to handle those, you got to go one step further. The 5 regions is a little bit complicated, but it's really just a combination of 2 and 3. You're going to have 2 atoms linear, and then the other 3 are going to be trigonal planar perpendicular to that. When you look at the shape, you see what we call a trigonal bipyramid. We call it a bipyramid because you can look at the pyramid going up to the top atom and down to the bottom atom with the two little pyramids pointing in opposite directions. That's trigonal bipyramid. The last one is 6 regions. And when you get up to 6 regions, you get something that should look somewhat familiar if you've ever studied X, Y, Z coordinate planes and coordinate points. Everything's 90 degrees apart or 180. It's like the X, Y, and the Z axis of three-dimensional space. You put one atom in each space, you get 6 total. Bond angles are either 90 or they're 180. You might go, why did octahedral when there's...
So for me, seeing something like that doesn't really help me because it still looks kind of flat. I mean, I get that that one's out front and that one's out back, but it still doesn't give the full thing until it starts to spin. Spin. oxygen?
6. Well, if you close up, if you take every point and make a line, you get a closed three-dimensional object with a total of 8 sides. 8-sided enclosed figure is an octahedron, and so we call it an octahedral geometry. So those are the other two that are part of VSEPR theory. When you put all 5 of those together, you've got all 5 of what we call our.
So I'm going to stop it there. It's not enough what he has there because these are just showing all the possible valence electrons bonded to another atom. But there's 2 other shapes that are super important that have lone pairs, and he doesn't have that on this video. And so I just want you to be aware of that. This is all great and fine. And those last 2, those are, do you remember when we were doing dot diagrams for the first time? I said there's exceptions to the octet rule. So there are some atoms. Occasionally there's a compound with nitrogen at the center, and nitrogen has 5 valence electrons, and it can bond 5 times. Sulfur can bond 6 times. It's possible. Not phosphorus, not nitrogen. Phosphorus can bond 5 times. Sulfur can bond 6 times. They happen. They're real. You have to account for them somehow. They break the octet rule, but those are their shapes, those last 2 that he was talking about. All right, stop there and go on with the show. So this picture shows there's 8 of them. How did that go there? There we go. So linear, 2 things on the central atom, trigonal planar, 3 things on the central atom. What he didn't talk about is trigonal bent, which we usually just call bent, or bent triatomic. We just call bent for the water molecule, or anything with when oxygen just has 2 things bonded to it, or sulfur. The trigonal pyramidal is what our book calls it. This picture just shows pyramidal. Tetrahedral, super important for carbon. The bipyramidal, trigonal bipyramidal. So again, the 3 in the middle, like trigonal planar, and then the linear through the middle. And then octahedral. There's 2 others on this one. I've never seen these. I don't know why they're on there. Maybe there's molecules that are T-shaped, but I don't know why that would be. Okay, I think that's wrong. But anyhow, so we're going to go to this, and I'm going to apologize right now because this is kind of wonky. I'm going to use my little pad, but it's not super great and not very fine writing, and it also is really small on my screen because it's showing me both slides for the PowerPoint. Even though it's huge on here, it's really hard for me to write on here. So again, my apologies in advance for my terrible penmanship. So this first line, you're going to end up dividing in half most of it, but not all of it. And so here's the cool thing. Those of you at home, find a periodic table. Those of you in the classroom, look on the walls. We've learned a lot about just where the position is of an element on the periodic table can tell us about its electrons. Group 1 has 1 valence electron. Group 2, 2 valence electrons. Ignore the transition metals. Group 3A or 13 has 3 valence electrons, 4 for carbon. Those electrons are all available to bond with somebody. Knowing where they are in the periodic table, every element in group 1 ends with an electron configuration of S1. Lithium's 2s1, sodium's 3s1, potassium's 4s1, etc. Okay, everybody in group 2 ends with S2. Everybody in boron's family ends S2p1. Carbon's family, S2p2. So you know that from doing electron configurations. Well, the cool thing is it could tell you about shapes as well. So we're going to start with lithium. And lithium only has 1 valence electron, so all it can do is bond once. So I'm going to draw a 1, and then I'm going to draw a dashed line underneath it on this little box. You can make a whole separate box if you're doing this by hand. How many lone pairs does lithium have? None. It only has 1 electron. It's in group 1. And again, I can't do straight lines very well. We'll come back to type of hybrid in just a second. Bond angle. It can only bond once. So the simplest compound is lithium with hydrogen, okay, lithium hydride. And so what's its dot diagram going to look like? Lithium gets 1 dot, hydrogen gets 1 dot, crazy. It's supposed to just click my little pen and I can't get it to do that. So again, hydrogen gets 1 dot. Okay. Oh, my screen went blank on my computer. So how is that going to make a molecule? Well, if we put them together, one side's going to have the hydrogen, the other side's going to have the lithium. If you do that, obviously, I hope the shape of this molecule is 2 points make a straight line, right? Basic geometry here. So it's a linear shape, okay? And you can write linear in this whole box because the next one's also going to be linear. So he didn't even talk about it when there's just 2. Okay, and again, I'll come back to this, but anything linear is 180 degrees. So remember S, that's supposed to be an S, believe it or not. And then there's 3 P's, right? So group 1, they all end with S1. They just have 1 electron. There's no hybrid going on for group 1 elements. There's nothing to hybridize. There's nothing to mix with. All right, let's get next door to lithium, and that's beryllium. This is group 2, and they have 2 possible valence electrons. They can bond twice. No lone pairs again. Now, really, one of these years I'm going to remember to make this so it doesn't look like that. Anyway, beryllium, hydrogen together is perfectly legitimate compound. Again, beryllium is going to be the central atom. So this is like the one that he had on his video. And then the hydrogens are going to be on either side. Why are they not going to be at 12 o'clock and 3 o'clock, for example? Why wouldn't we put them at 90 degrees? Our electrons are fighting against each other, repulsion, right? So it's going to spread out as far as possible and make a line. Okay. So I don't know how you would type that onto your document, but and that's going to get crazier here in a sec. So the next element, so group 1 and group 2, remember we're sticking with the valence electrons, S and P block elements. So jump over the transition metals, and the next one is boron. It's in group 3, which is 3A or 13. They have 3 valence electrons, so it can bond 3 times. Whether it's boron, aluminum, gallium, they can all bond 3 times. Again, no lone pairs. Okay. And oops, I'm so sorry. Let me go back up to beryllium. So type of hybrid. So beryllium has S2 is what it ends with. However, those electrons have a buddy now. So that doesn't work, right? It shouldn't pair at all, but they do. So let's see if I can do this without erasing the whole thing. Oh, there we go. It took the circle too, but that's fine. So what ends up happening for beryllium, come on, there we go, is we get 1 electron in an S, 1 in a P, but it's not really an S and a P, it's a hybrid. The S spherical and the P dumbbell smush together and make an S-P hybrid. Sorry, I cannot write this thing. Oh, that's awful. Okay, one more time. SP, that's a little bit better. Okay. So boron is S2P1, but guess what? This other electron is going to end up going here into a different p orbital. Okay, so you're going to end with SPP, but we don't write anything twice. This is not a very fine control, sorry. So SPP becomes SP. 2, right? It's not squared, there's 2. The 2 P's and the S all smush together to get 3 equivalent hybrid orbitals. This time the bond angle is 120. You can also put boron with 3 hydrogens. And so again, if you did dot diagrams, the boron will go in the middle, boom, 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 and then hydrogens would bond on there. And then on your paper, it looks like they're all 90 degrees apart, which they are not. Okay, they're not at 9 o'clock and 6 o'clock and 3 o'clock. In reality, they're 120 degrees apart with boron in the middle. There has to be an easier way to do this. Boop, boop, boop. Okay. And what's the name of this one? Read. What's the prefix for 3? Tri, good. So this is trigonal. And it's a flat molecule, so it is planar. Good. Wow, that's awful. I apologize. I think I'll make separate lines for tomorrow so that it's easier to see. All right, last but not least, and this won't take too long, I don't think. Carbon. How many times can carbon bond? How many valence electrons? And again, carbon is S2P2, but again, one of those P electrons is, excuse me, one of those S electrons is going to move up to a P. Again, carbon does not have lone pairs. It's group 4A or 14. Because the 2 electrons in the S orbital move. Ooh, I did it that time. How about that? We end up with SPP, P, 3 P's and the 1 S all smushed together to form 4 identical shaped orbitals. That's a SP3 hybridization. What's the crazy bond angle for this? I always thought it was so weird. You guys, 109.5. Good job. That half degree thing. What a weirdness. That's chemistry for you. But remember, it's in 3-dimensional space. It's not just 120 of a flat circle. It's in a sphere. Okay, so the simplest compound is methane. I'm just going to draw it down here if you'll forgive me, and then just understand it's supposed to go. Oh, I'll just erase it. Never mind. I'll make it. Otherwise, it'll get confusing for somebody. Okay, I'm just going to erase this stuff to get it out of my way. All right. Oh, wait. So carbon is in the center. Normally on a flat piece of paper, when we're doing our dot diagrams, we're going to just draw carbon 1, 2, 3, 4. I'll put my carbon over here right now, and then throw in our hydrogens. And again, when we do this on a flat piece of paper, it looks like a little plus sign because it's flat, but it's not really flat. And so when they do these in textbooks and stuff, they'll put, you know, a hydrogen. They'll do some little wedgy looking thing to try and give you the perspective that there's something out here. They'll do a little dash line to make you understand that it's behind it. And maybe they'll do another plain line. So they get this weird looking, that's supposed to be this, okay? And I don't know how, it's really hard for my brain. So what's the name of carbon? Carbon's molecule shape. What's prefix for 4? Tetra, okay, tetrahedral, good. So this is a tetrahedral shape. Okay. So tomorrow we'll talk about the 2 with lone pairs, and then we'll talk about those 2 exceptions, but not today. And again, all these shapes are possible because the orbitals, the spherical and the peanut orbitals, hybridize or blend together to make something new and different and wonderful. Questions? Okay. Questions from the home front? Sorry about my terrible handwriting. Anybody need some questions answered? All right, I'll call it a day. Have a wonderful Thursday evening.